On this video, we're going to review some of the work from algebra on simplifying radicals and then refresh your memory on some of the geometry stuff that we're going to need. So to simplify radicals, we're looking for perfect squares that divide into, say, 98 evenly. So if you scratch your head a little bit, you can see that 98 is 49 times 2. Square root of 49 is 7, so that becomes 7 square root of 2. And that's our simplified version of the square root of 98. And similarly, we can do some arithmetic with these. So we can't add these we can't add these radicals when they're not the same radicands. That's the thing inside. But we can simplify first. So 50 is 25 times 2. So we can say the square root of 25 is 5 times that other 2 that's outside the radical is going to make that be a 10 square root of 2. And we did the square root of 98 a minute ago. That was 49 times 2. And the square root of 49 is 7 times 3 is 21. Now, since these are both square root of 2's, we can add them. It's like 10x plus 21x. So that will be 31 square root of 2. Now, we can only add and subtract like radicals, but we can multiply just about anything. So we can multiply the outsides. The 2 times 3 is 6. We multiply the radicands, the inside, and that's 18. Then we see if we can simplify that any further. And in this case, since 18 is 9 times 2, we can say the square root of 9 is 3. The 3 times the 6 is 18 square roots of 2. The next one, to square that, means we're just going to take the 3 square root of 2 times 3 square root of 2, or you can think of as squaring the 3 and getting 9, and squaring the square root of 2, which is going to be just 2, and we get 18. You may remember rationalizing the denominator, so it's not considered correct or simplified to leave a radical in the denominator. We can fix that if we multiply top and bottom by square root of 5. That's multiplying by 1 in a strange form. The numerator becomes 2 square root of 5. The denominator becomes just 5. Okay, so let's talk about did I have another one? I thought I had another one. I guess not. Okay, so let's do our Pythagorean Theorem. So you hopefully remember that if we call this triangle ABC, so we label this where the vertices go opposite the angles. So the angles are named with capital letters. The sides opposite those angles get small case letters. So in the Pythagorean, a right triangle, the hypotenuse squared is the sum of the squares of the legs. So the two sides that make up the right angle are known as legs. Now, the way theorems are stated, and the Pythagorean theorem is no different, it's as an if-then statement. So if the triangle is a right triangle, then c squared equals a squared plus b squared. The converse isn't always true in every theorem, but in the case of the Pythagorean theorem, it is, which means if one side length squared is equal to the sum of the squares of the others, then it must be a right triangle. So we can check this out by trying to plug that in. So if we take the square root of 30 squared, and I'm going to ask the question, is that equal to 2 square root of 3 squared plus 3 square root of 2 squared? If it is, then the blue triangle here is a right triangle, and if it is not, then it's not a right triangle. So square root of 30 squared is just 30. The 2 square root of 3 squared, we're going to get 4 times 3 is 12. And 3 square root of 2 squared is 9 times 2 is 18. And sure enough, they are equal. So the answer is yes, that is a right triangle. Okay, So 45, we have some special triangles, and 45, 45, 90 triangles are one of those special triangles. These are also, you might note, isosceles triangles. So in your geometry days, you know that if two angles are congruent, then the sides opposite those angles are congruent as well. So this is also known as an isosceles right triangle. Now we can see that because it's isosceles, if we call these two side lengths x, and I don't know what the hypotenuse is yet, but we'll figure that out, then we can say from Pythagorean Theorem that c squared is x squared plus x squared, so c squared is 2x squared, so c is the square root of 2x squared, which is x squared of 2. So the takeaway is that there is kind of a formula for finding side lengths in a 45, 45, 90 triangle. We always know the two legs are going to be x, and the hypotenuse is going to be that side length of the leg, x times the square root of 2. So in particular, if we look to this yellow triangle with one side length 7, and we want to know what m is going to be that side length 7 times the square root of 2. And there you have it. Now we're going to have to do a little bit more work on the next one, on the green triangle. So the hypotenuse is 10, which we can set equal to x squared of 2. We can solve that for x by dividing by square root of 2. We can then rationalize the denominator and get 10 square root of 2 over 2. And finally cancel the 10 with the 2 and call that 5 square root of 2. And so that means that that side length n is 5 square root of 2. Now let's talk about 30, 60, 90 triangles. So in a 30, 60, 90, we're going to start with an equilateral triangle. All three sides are the same length. I'm going to name those side lengths 2x because that's going to make the work go a little bit easier here. If we drop a perpendicular down to one of the opposite sides, then that splits the one original equilateral triangle into two congruent 30, 60, 90s. So an equilateral triangle is also equiangular. So we know these are 60 degrees. Dropping in that perpendicular is going to divide these into two 30-degree angles. So if we just look at one of those, we can see that the hypotenuse here is 2x. We bisected this opposite side here, which was 2x originally, which means that's going to be x. I'm going to call this b, and we can do a little Pythagorean theorem to see what we're going to get for that b in terms of x. So if we square that out, we're going to get 4x squared. Subtracting that x squared to the other side gives us b squared is 3x squared. And when we simplify that radical, we get x square root of 3. And so what we take away from this is that the side lengths in a 30, 60, 90 triangle, we call now here's our right angle, we call the shorter leg, we call that the short leg. So there's the two sides that make up the right angle are the legs, and so this one is going to be the long leg because we can see that square root of 3 times x is bigger than square root of 1 times x. And then, of course, the 2x is the hypotenuse. Some people get confused about which is bigger, but you can see that between x and x times the square root of 3 and 2x, that this is like, that x is like square root of 1 times x, and then we have the square root of 3 times x, and then 2 is the square root of 4 times x. So you can see the sides go in the same order opposite the angles. So the shortest side is opposite the smallest angle. The middle sized side length is opposite the middle-sized angle, and of course the hypotenuse is the biggest, the longest side, and that's opposite the biggest angle, the 90-degree angle. let's see how we can use that. So let's look at this yellow triangle. Now the x is the hypotenuse, or the 8 rather, is the hypotenuse. So that tells us that 8 is equal to 2x. We solve that and find out that x then is equal to 4. Now that's the short leg, which means it's going to be that side opposite the 30-degree angle. So that means that m must be 4. N is the long leg. It's opposite the 60-degree angle. That's x times the square root of 3. We just said x was 4, so that's going to make n equal to 4 square root of 3. All right, let's try it on the next one. Now the green triangle, we see that the side that we're missing, or the side opposite 6, the angle opposite 6, must be the 60-degree angle. That's the long leg, so that means our 6 is equal to x squared to 3. We can solve for x by dividing by the square root of 3. That's going to give us x equal to 6 over the square root of 3. We can rationalize that, and that's going to become 6 square root of 3 over 3. Then we can cancel our numbers that are outside the radical, and that's telling us that x is 2 square root of 3. Well, x is the short leg. That's the one opposite the 30-degree angle. That means that n must be 2 square root of 3. And the hypotenuse, that's the m, that's 2x, and 2 times 2 square root of 3 is 4 square root of 3. And we figured out what m and n are. Now the next one, that red triangle, got all kinds of stuff going on here, because now we have a 45-45-90 and a 30-60-90. What great fun. So we're going to try to find n. We need to figure out what this side length is right here, that side length that is shared by the 45-45-90 and the 30-60-90. In the 45-45-90, the hypotenuse is x square root of 2. So we can solve for x by dividing by the square root of 2. So we're going to get x equals 6 square root of 3 over square root of 2. We're going to rationalize that and multiply top and bottom by square root of 2. The square root of 3 times square root of 2, we can multiply those. That's square root of 6, and in the denominator we get 2. We can cancel that 2 in the denominator with the 6 that's outside the radical, and that's going to become 3 square root of 6. Now that x, what we called x there, is this shared side right there. That is 3 square root of 6. Now we turn our attention to the 30-60-90 triangle. That's the one down below. Now this side 3 square root of 6 is opposite the 60-degree angle. That means that 3 square root of 6 is equal to x times the square root of 3. So we can solve for x by dividing by the square root of 3. So we're going to get that 3 square root of 6 over square root of 3. Now you can, just like you can multiply the insides of the radicals, when you are dividing by them, you can do that division. And so that is actually going to be 3 square root of 2. It's kind of a pretty painless way of doing that. Now that's our x. So in our scheme, in that triangle on the bottom, the 30-60-90, the x is the short leg, and this is our 30-degree angle here. So that means we found this side length is 3 square root of 2. We're trying to find n, which is the hypotenuse. And the hypotenuse we know is 2x, so our n is going to be 2 times that 3 square root of 2, which is going to be 6 square root of 2. Wow, that's pretty cool. Do I have any more of these gems here? I think that's it. Let's see what the next panel holds for us. And let's scroll down a bit. So now we're going to move to the Sohcahtoa thing. Hopefully you remember this from your, I think you did this in geometry days. So Sohcahtoa is just a way of remembering what sine and cosine and tangent are. So sine, the word sine is S-I-N-E. We abbreviate that S-I-N, and you always have to take the sine of an angle. So the sine of angle A that's going to come from this part of our Sohcahtoa. So that's supposed to tell us that the sine of, so there's the S, the sine of an angle is the opposite side over the hypotenuse. And so in our particular triangle here, since our angle A is down here, the opposite side of that angle A is going to be side length A, so that's going to be a little a, and the hypotenuse is the C. So our sine of angle A is A over C. It's the opposite over the hypotenuse. The cosine of A comes from this part of Sohcahtoa, and that's telling us that the cosine is the adjacent side over the hypotenuse. For angle A, the adjacent side, the two sides that make up the angle, one of them is the hypotenuse, the other one is the adjacent side, so that's going to be the B, and the hypotenuse is the C. So the cosine of angle A is B over C. And the tangent of angle A, that comes from the toa part. That's saying that the tangent is the opposite side over the adjacent side. And so for angle A, the opposite side is side A, and the adjacent side is side B. So there's our tangent of angle A. Now we can do the same thing for other angles. So the sine of angle B, if we direct our attention over there to angle B, sitting over here, then sine of angle B is going to be, again, opposite over hypotenuse. Opposite is the B, and the hypotenuse is the C. Notice that the sine of angle B is the same as the cosine of angle A. That is not a coincidence. That is because angle A and angle B, because they are the other two angles in a right triangle, those two angles must add up to be 90 degrees. You may remember that angles that add up to be, the two angles that add up to be 90 degrees are known as complementary angles, or they're complements of each other. So cosine of angle B is its adjacent over the hypotenuse, and the adjacent for angle B is A, and the hypotenuse is still C, and we can see that the cosine of angle B is the same as the sine of its complement. That's where the name sine and cosine come from. Those are called cofunctions, and so that's always true. So the sine of a 20-degree angle would be the same as the cosine of its complement. 90 minus 20 is 70. So the sine of 20 is the cosine of 70. And the tangent of B is going to be opposite over adjacent. So the opposite is side length B, and the adjacent is A. Okay, so grab a calculator, and if you're using a rental, then anytime you use one of ours, if you borrow one in the class, you're going to need to check the mode, because in AP Calculus, we live in radians 100% of the time, whatever that means. But at least to start with here, we need to be in degree mode. That will change as we go further into this. So we're going to try to solve for the missing side length in this case. So these three pieces, the x, the side, the 6, and the angle, the trig function that connects those, because for that 24-degree angle, the x is the opposite side and the 6 is the adjacent. From Sohcahtoa, we know that the tangent of 24 degrees is opposite over adjacent. So that means that if we solve for x and multiply that 6 to the other side, then we can, in our calculator, go 6 times the tangent of 24. And if you're in degree mode, what I'm getting to 3 decimal places is going to be 2.671. Hope you're getting the same thing. In the next one, now what we have is for that 52-degree angle, 7 is the adjacent side and x is the hypotenuse. So the trig function that connects an adjacent to a hypotenuse is a cosine. So we have the cosine of 52 degrees is the adjacent over the hypotenuse. So I'm going to do a little bit of arithmetic or algebra here first. I'm going to think of multiplying that x to the other side and then dividing by the cosine. So to figure out what side length x is, we're going to have to take the 7 divided by the cosine of 52 degrees, and that looks to 3 decimal places like it's going to be 11 point. I'm getting 3698, which is going to go to 370, and so that is our value of x. So on the next one, if we see that for this angle x, the 5 is the opposite and the 8 is the adjacent, so the trig function that connects opposite and adjacent is going to be a tangent. So from Sohcahtoa, tangent is opposite 5 over the adjacent 8. Now to solve for the angle, what we have to do is take the inverse tangent of 5 over 8. So on our calculator, that means we're going to do the second tangent and then go 5 divided by 8, and that is going to be, it looks like 32 point, I've got 005, and that's in degrees. So our angle is going to be about 32 degrees. One last little thing, you will have to talk about an angle of elevation and an angle of depression at times. So what we mean is by an angle of elevation, whatever that horizontal is from your line of sight, if you look up from there, that angle is the angle of elevation. And if you are looking down, that angle that goes from your horizontal line of sight that goes down to what you're looking at, that's called the angle of depression. All right, that should do it.